can unmute yourself.
Oh, okay. Hello. Test. Oh, seems good. I think so.
All right, great. Then let's go ahead and get started with the discussion. So we're really happy to have Josh Alman. Josh is an expert on matrix multiplication and algorithms and complexity theory. He's been doing lots of really great work. He's also got the honor, rare among theoretical computer scientists, of being featured in a popular webcomic. Together with Jamie Williams. But I'm told Scott Aronson has also appeared in
I think so, yeah.
Anyways, today Josh is going to tell us about some really cool work on designing smaller arithmetic circuits for interesting linear transformations like the Walsh-Hadamard transform. So, Josh, please.
Hello, everyone. Can you hear me okay in the back? Good. Yeah. Okay, so today I'm going to tell you about the Walsh-Hadamard transform and matrix rigidity. These are topics I've been working on for a while, so I'm going to tell you kind of an overview of a few different results. And many of them are joint work with a bunch of great students who've come to work with me at Columbia over the years. There's Yunfeng, who was a master's student at Columbia, Baiqian, who's now my PhD student, Jingxun was an undergrad, Ashwin also an undergrad, and Kevin was a master's student. Yeah. Okay, so what is the Walsh-Hadamard transform? It's a family of matrices of size power of 2 by the same power of 2, whose entries are -1s and 1s, defined recursively like this. So here's the 2 by 2 Walsh-Hadamard transform is 1 - 1 1 1.
Oh. Sorry, there is a problem in the streaming. I need to fix it.
Oh, okay. There's a problem with the streaming.
Okay, this is.
Works.
Sorry.
Is this okay? There we go. Yes. So this is the first one, and then afterwards, each one is recursively defined, where you take 4 copies of the previous one, but you negate the top right copy of it. So here's a picture of the first few of them. Okay. So this is the Walsh-Hadamard transform that I'm going to tell you about today, and I'm especially going to focus on the problem of like computing the linear transformation defined by this family of matrices. So the algorithmic problem where you're given as input a vector of length n and you want to compute hn times that vector of length n. Actually everything I'm going to talk about today works over any field. You could think of like the reals or the complex numbers. I think the problem is kind of trivial if your characteristic is 2, so maybe the characteristic shouldn't be 2. And you know, like is typical in this workshop, I guess I'll count the number of arithmetic operations that the algorithm does. For any basically matrix vector multiplication problem, there's a trivial like n squared operation algorithm. You just follow the definition of matrix times vector multiplications, and our goal is going to be to do better than that. Okay, so why do I care about this? Well, the Walsh-Hadamard transform is kind of a discrete version of a Fourier transform. It has applications in a lot of the same places that other Fourier transforms you might be familiar with come up. It's in signal processing and data encryption and compression and so on. It really shows up in a lot of other places too. Like if you know anything about quantum computation, you know it's like a basic gate in that area. It shows up often in algorithms and complexity, like in communication complexity. This is the communication matrix of the inner product mod 2 function. Just to say a tiny bit of detail about one example. So there's this problem of like given as input a multilinear polynomial, so like a polynomial p in n variables. So it can be described by its vector of coefficients, which is a vector of length 2 to the n. Maybe you want to evaluate this polynomial on all -1, 1 points. And the way to do this is exactly to multiply the Walsh-Hadamard transform times that vector. So if you're familiar with this, many people in like Boolean function analysis study the like Fourier analysis of the Boolean hypercube. This is exactly the Fourier transform that they're studying there. And it's also used as a subroutine in the best FFT algorithm, which I'll tell you about in a couple of slides. Okay, so this is the Walsh-Hadamard transform. How do we compute it? Well, there's this very simple folklore fast Walsh-Hadamard transform algorithm. This is like the simplest recursive algorithm you could ever come up with, where if we have a vector and we want to compute the Walsh-Hadamard transform of the vector, we split it into 2 vectors of length n over 2. And we recursively compute the Walsh-Hadamard transforms of the 2 parts of size n over 2. and then combine them. At the top you add them, and at the bottom you subtract them. I think I moved where the minus sign is. Okay. So this is a very simple recursive algorithm, and it has this recursion that you can solve. So to do a transform of size n, you do 2 transforms of size n over 2 plus n operations, not even O of n, but n operations. There's n over 2 additions and n over 2 subtractions, which solves to a total operation count of n times log base 2 of n. And it's really 1 times n times log base 2 of n. Okay, and the 1's going to be important. So this is the fast Walsh-Hadamard transform, and I'm going to really focus on a slightly different way of thinking of this algorithm today, which is as a sparse matrix factorization. Okay, so here's, you can kind of equivalently view this idea as a way to factor the Walsh-Hadamard transform matrix as a product of a bunch of sparse matrices. So here's the idea, here's the recursive definition again. And I can write it out like this. I can write it as the product of 2 matrices, the first with 4 blocks of identities where I've negated one of them, and the second is like a block diagonal matrix with 2 blocks of the n over 2 Walsh-Hadamard transform. You see, you just multiply those 2 together and you get the same thing from above. And this is nice because the first matrix on the left with the identities is a very sparse matrix. It only has 2 non-zero entries in each row or each column. And then you could do it again. We can, again, like write the hn over 2s with these blocks of identities and hn over 4s, and so on. And when you keep doing this, you'll eventually get a product of log n different matrices where each one just has blocks of identities. So each one has only 2 non-zero entries in each row and each column. So it's a product of very, very sparse matrices. So a factorization like this, I'm going to call a linear circuit. Really, in the literature, it's a synchronous linear circuit. And how do we measure its size and its depth? Its size is going to be the sum of the number of non-zero entries in each of the matrices, and its depth is just the number of different matrices in my factorization. So like, why do I say that's the size? Well, if you want to multiply the matrix times the vector, you can just one by one from the right to the left multiply all the sparse matrices by the current vector, and the total operation count will be order of this size. Okay, so these are what I'm going to be talking about. And using this idea I just showed you, we saw that the Walsh-Hadamard transform has a depth log n circuit of size n log n. You can also, I'll show you more details in a second, make this a lower depth circuit. So for example, you get a depth 2 circuit of size n to the 1.5 using the same idea. Okay, so this is like the basics about the Walsh-Hadamard transform. And what I want to tell you about today is mainly 2 different improvements to this simple recursive idea. So here's the first one is a smaller depth 2 circuit. So I just mentioned, and I'll show you the details in a moment, that the fast Walsh-Hadamard transform idea gives a circuit of size n to the 1.5. But in this line of work, together with Yunfeng Guan and Ashwin Padaki and Baitian Li, we got it down to n to the 1.45. So this is the first result I'll tell you about. And beyond just like being nice to make smaller circuits, this result I think is particularly cool because it gets around a barrier. So there's this result by Pavel Pudlak from 2000 who showed that actually depth 2 so-called bounded coefficient circuits for the Walsh-Hadamard transform require size n to the 1.5. What do I mean by that? So if we're working over the complex numbers, there's lots of coefficients in our circuit, which are the non-zero entries of all these sparse matrices I'm talking about. And for example, the circuit I just gave you, all the entries are just 1s and -1s. So it's a bounded coefficient circuit because all the entries are numbers of at most constant magnitude. And if you think about the standard algorithms we know for discrete Fourier transforms and so on, they're pretty much all bounded coefficient circuits. So Pudlak showed that if you have a depth 2 bounded coefficient circuit, it really needs n to the 1.5 size. And so we are able to circumvent this barrier. And I think this is the first non-trivial result that circumvented one of these bounded coefficient lower bounds. So we'll see later the big coefficients that are going to show up. But they're not so big. They're really like log n bit integers that are going to be the coefficients. In fact, they'll all be powers of 2. Okay, so that's the first result I'll tell you about. And then the second one is when I don't care about the depth anymore, I'm going to give you a new algorithm that uses 0.96 times n log n plus order n operations. So improving the constant 1 I emphasized before to 0.96. So this is I think this is particularly nice because the fast Walsh-Hadamard transform is like such a simple algorithm that we can improve it at all. But one particular application I'll tell you about for one slide is that we can use this to speed up the more usual FFT algorithms also. So let me tell you just a tiny bit about that.
Is also a lower bound for bounded coefficients, right?
Yes, it's further away from what we get though. Yeah,
Ah.
yeah. It's like, I forget the number, but it's less than 0.96. Yeah. Okay. So here I'm probably just in the interest of time not even going to define what exactly I'm talking about here, but I'm guessing most of you at least kind of know. I'm talking about the question of, what's the best leading constant I can get? What's the smallest constant A, so that the power of 2 cyclic group discrete Fourier transform that people usually talk about can be computed with A times n log n arithmetic operations. So there's been a bunch of work on this problem. Probably if you learned about the FFT algorithm in like algorithms class, you learned the Cooley-Tukey algorithm that gets a constant of 5. And a few years later, Yavne used this cool split radix idea to improve it to 4. And that was the state of the art for a while until there was this neat result of Van Buskirk who improved it to 3.777. Actually, I'll tell you a very short story about that one. Is apparently the way Van Buskirk announced his new FFT algorithm. He didn't like publish a paper about it or something like this. He just wrote code that seems to correctly compute the FFT in this many operations and posted it to Usenet, which was like the Reddit of the time, And he posted it in 2004, and it took people 3 years after that to actually like prove it was correct and analyze its operation count and so on. And a few different groups gave different explanations in 2007 that it really got 3.777.
Did he claim something about, like, what did he claim on the Usenet?
He just claimed, I think he just like said it's faster. Like he counted the operations for some input sizes and it was smaller, and it started a lively discussion. And then in 2017, Sergeyev improved this a little bit. He found a way to kind of take the radix ideas of this Van Buskirk algorithm to the limit in some sense and give a slight improvement even more. So in this paper with Kevin Rao, we give a kind of weird like partial reduction from some of the parts of these best known FFT algorithms to the Walsh-Hadamard transform. So what we show is this. If you can compute the Walsh-Hadamard transform with a leading constant of C, then you can compute this discrete Fourier transform with a constant 2/3 C plus 28 over 9. Okay? Roughly, if you know about this stuff, the 28 over 9 comes from all the twiddle factor things, which we don't touch, but the 2/3 C comes from the additions and subtractions that we somehow rearrange into Walsh-Hadamard transforms. So if you plug in C equals 1, like the folklore algorithm, you exactly recover the 3.777. But if you plug in our new 0.96, you get our new leading constant, which is 3.75. So we got a nice improvement to the FFT. And these, I know that, they're, much of my work is about making very small improvements to constants. But some of these algorithms really are used. Like this modified split radix is actually implemented and used in a popular FFT package called FFTW, which stands for Fastest Fourier Transform in the West. But you can look through their code and see they've really implemented and used this in practical FFT. And ours is, hopefully you'll see it's not like, we're not doing anything super complicated. So I hope ours might be able to help a little bit also. Okay, so that's all I'm going to say about the FFT. Let me get into actually showing how our better Walsh-Hadamard transforms work. So I'll start with the new depth 2 circuit, which again, my goal is to factor the Walsh-Hadamard transform as the product of just 2 sparse matrices. So in our papers, we get down to an exponent of 1.45. In this talk, I'm mostly just going to tell you how to get to 1.49, which will be a bit simpler, but I'll tell you at the end some recent ideas that got the exponent rather down a little bit. Okay, so the key notation that I suspect in this audience you all have in the back of your minds is that we should really be talking about Kronecker products here. So for 2 matrices, if you have an A by B matrix X and a C by D matrix Y, their Kronecker product is an AC by BD matrix. it's defined in this way. So for each pair of a row of x and a row of y, there's a row of the Kronecker product. For each pair of columns, there's a column of the Kronecker product, and the entry is the product of the entries. So here's an example, and just for any pair of an entry from one and an entry from the other, there's an entry whose value is the product of those entries. Why is this? And if you're more familiar with like the tensor products, this is the tensor product, but then you flatten it down to a matrix at the end instead of letting it grow in dimension. So there are two really nice facts about the Kronecker product we're going to use today. The first is that the Walsh-Hadamard transform is indeed a Kronecker power. So you can check the recursive definition I gave you before is exactly the same as saying it's the n by n Walsh-Hadamard transform is the log base 2 of nth Kronecker power of the 2 by 2 Walsh-Hadamard transform. Okay. And the second is the Kronecker product has this nice property called the mixed product property, which this is a slightly special case of it. It says that if you have any matrix and you write it as a product, A times B, then the mth Kronecker power of the matrix is also equal to the product of the mth Kronecker power of A and the mth Kronecker power of B. So this is not, this is going to be very useful to us on one hand, but it's not like a really deep fact with a hard proof. You just kind of write out the definitions of these things and check that it's true. But we're really going to make use of this. And in fact, the idea is that if we have a nice depth 2 circuit for a matrix M, this automatically gives us a depth 2 circuit for any Kronecker power of M as well. So in order to make a good depth 2 circuit for all Walsh-Hadamard transforms, it suffices to make a good depth 2 circuit for any fixed Walsh-Hadamard transform. And that's the approach we're going to take. And I'll mention, this will come up a little bit later, this is what people usually actually call the mixed product property, this more general statement that you can interchange the Kronecker product and the usual product of matrices, assuming the dimensions of A, B, C, D are such that these products all make sense. So this will come back a little bit later. Okay, so let me tell you, I told you there's like a simple size n to the 1.5 depth 2 circuit for the Walsh-Hadamard transform. So let me tell you how it works. We're basically just going to do one step of that way of turning the Walsh-Hadamard transform into a product of log n different matrices. We're just going to do one step of it. So here's one step. Here's the 4x4 Walsh-Hadamard transform. And I'm writing it as the product of two different matrices. And you can see that each of these is a matrix with only 8 non-zero entries in it, even though they're 4x4 matrices, so they have 16 total entries. This is the whole idea. And then we're going to apply the mixed product property. So that means that for any n, which is the n by n Walsh-Hadamard transform is the log base 4 of nth Kronecker power of the 4x4 Walsh-Hadamard transform. So we can write it as the log base 4 of nth Kronecker power of these two different small matrices I've written right here. So this is a depth 2 circuit because it's the product of two matrices. And its size is just the number of non-zero entries of these things. You can check easily the number of non-zero entries is multiplicative under the Kronecker product because the entries are just product of original entries. So this is exactly, the size is exactly going to be 8 to the power of log base 4 of n, which is exactly n to the 1.5. So this is just doing one step of the idea from before it gives you size n to the 1.5. And our goal is going to be to improve on this. So again, kind of like I said, the plan is we're going to construct an improved depth 2 circuit for a fixed Walsh-Hadamard transform. It'll end up being the 64 by 64 Walsh-Hadamard. So how are we going to do this? The idea now comes to the other part of the title of my talk, which is we're going to use matrix rigidity or matrix non-rigidity. What is this? So we say a matrix is rigid if it's far from any low-rank matrix in Hamming distance. So not only is it a high-rank matrix, but you have to change a lot of its entries before it becomes a low-rank matrix. So there's, of course, some parameters here. This is the usual way people write it. The rigidity of a matrix M for rank R, like curly R sub M for rank R, is the minimum number of entries you need to change in the matrix to make it rank at most R. And when we're changing the entries, we can change it to anything you want. It can change by a huge amount or a small amount or whatever. We're just counting the number of entries you change. So for example, if you take the n by n identity matrix, then for any rank R, its rank R rigidity is n minus R. Why is that? Well, it starts off as a full rank n matrix, but each time you change one of the ones on the diagonal to a 0, you decrease its rank by 1. So you can make it be rank R by changing n minus R of the 1s to 0s. And in fact, this is tight. Like one thing you can check is that when you change just one entry of the matrix, it can decrease the rank by at most 1. So you can't hope to do better than this. So actually, among all full rank matrices, the identity matrix is as not rigid as possible. By contrast, if you had, let's say, a random n by n matrix over F2, for example, but this generalizes, then it's very rigid with high probability. You likely have to change a constant fraction of all its entries to make its rank even slightly sublinear. So there's a whole challenge here of trying to understand the rigidities of interesting matrices and find rigid matrices. Yeah?
Is the rank here over F2 or R?
I guess in this example, F2, but it is true over R also. Yeah, if you had a 0, 1 matrix over the reals, this statement is also true. Yeah. Okay, so matrix rigidity was introduced by Leslie Valiant in the 70s. And he introduced it actually toward the goal of proving lower bounds for these linear circuits that I've been talking about. So what he showed is that if you have any n by n matrix that's computable by a very small circuit, a linear size log depth linear circuit, then from that you get a rigidity upper bound that you can change only n to the 1 plus epsilon entries of the matrix, and it changes rank to sublinear, like n over log n. So this is what Valiant showed, and he introduced this as a way to try to prove circuit lower bounds. So remember, for example, the Walsh-Hadamard transform has a depth log n but size n log n circuit. So if you wanted to prove that's optimal, one step toward that could have been, you'll see in a second, it's not going to work, to prove that the Walsh-Hadamard transform is too rigid for this to be the case. That would mean this is not the case and it doesn't have linear size log depth circuits. So this is kind of the inspiration for what we're going to do today, but we're going to pursue kind of a converse. So there's no formal converse of Valiant's result that's known, as far as at least known to me. But what we're going to do is nonetheless use rigidity upper bounds to give better circuits. So you convert a circuit into a rigidity upper bound, we're going to convert rigidity upper bounds into circuits. And we'll use products of Kronecker products properties of Kronecker products to do this. Okay, so what do we know about rigidity and the Walsh-Hadamard transform? Well, almost a decade now, actually, my advisor, Ryan Williams, and I proved that the Walsh-Hadamard transform actually is just not rigid enough to prove circuit lower bounds. So we showed that for any epsilon, you can change n to the 1 plus epsilon entries and get its rank all the way down to the n to the 1 minus epsilon squared. So it would have had to have been that when you change this many entries, you can't get its rank below n over log n. But we showed you actually can get its rank even further below that. So this is unfortunately not a great way to prove circuit lower bounds for the Walsh-Hadamard transform in particular. But one nice thing is there's a very kind of simple connection between rigidity and depth 2 circuits, that this kind of immediately gives some kind of depth 2 circuit upper bound. So the idea is that just for any matrix M and any rank R, the n by n matrix has a depth 2 circuit of size this, 2 times R times n plus the rank R rigidity of M. The idea is just, if you have a rigidity upper bound for your matrix, so you've written it as a low rank R matrix, which you can write as U times V for an n by R matrix U and an R by n matrix V, plus the sparse part, the part that you're changing to get down to that rank, which is a matrix S whose number of non-zero entries is this. And you can immediately see that see this as a depth 2 circuit, like U times V is a depth 2 circuit of size 2nr, and S is a sparse matrix. It's a depth 1 circuit of size n and z, of size the rigidity. So you have this, and then you balance it over R. Like as you increase R, 2nr gets bigger, of course, and the rank R rigidity gets smaller because your target rank is bigger, so you don't have to change as many entries to get to it. So you optimize over R, and you get some upper bound on the depth 2 circuit size, and you plug in our rigidity upper bound, and you immediately get that the Walsh-Hadamard transform has a depth 2 circuit of size n to the 2 minus delta first. I think it ends up being like n to the 1.95 or something like this. So on one hand, this is great because most matrices require n squared size linear circuits. So this is really, or whatever, truly quadratic size linear circuits. So this is really better than that. On the other hand, I just told you a few slides ago that the Walsh-Hadamard transform has a depth 2 circuit of size n to the 1.5. So it's not as good as this. I tried for quite a while, and I still, to this day, don't know how to use Ryan Williams. Use a different and way simpler rigidity upper bound instead. I'll show you the entire thing on this slide. In fact, I'm going to have a warm-up and the real thing all on this slide. Okay, so here's the warm-up. I'm going to prove to you that the rank 1 rigidity of the 4x4 Walsh-Hadamard transform is 4. All right, here's my proof. So on the left is the 4x4 Walsh-Hadamard transform. On the right is a rank 1 matrix. You can see it's rank 1 because every row below the top one is the negation of the top one. And you can check that they differ in 4 entries. So that shows the rank 1 rigidity is at most 4. In fact, it's exactly 4. And there's a nice simple proof of this, which is you can take the 4x4 matrix and partition it up into these 4 disjoint 2x2 matrices. And each of these 2x2 matrices has full rank. So you have to change at least 1 entry in each of them if you want the whole thing to have rank 1. Like if you have a rank 2 submatrix, the whole thing will have rank at least 2. So you have to change at least 1 entry in each of those parts, and they're disjoint, so you have to change at least 4 entries. So this is actually tight. Okay, so that's the warm-up, and here's what I'm really going to use, which is the rank 1 rigidity of the 8x8 Walsh-Hadamard transform is 22. And here's the upper bound proof, and it looks the same. It's just, taking advantage of the first column and row of 1s, basically. This is also tight. I don't have as snazzy a proof that this is tight. Actually, I wrote some code to do a big brute force search and verify that this is tight. And I want to emphasize, I did this back in like 2021, which was before ChatGPT. So I wrote this code all by myself. Okay. But there you go. And this is really the whole rigidity of what we're going to use. Okay. So how do we go from this to a circuit? Well, so I just showed you this rigidity upper bound, which is the 8x8 Walsh-Hadamard transform, because it's rewritten as the sum of a sparse matrix and a low-rank matrix. The low-rank matrix, it's rank 1, so it's like the outer product of 2 vectors of length 8. The sparse part, it had 22 non-zero entries. The rigidity was 22. So we're going to, like before, turn this into a depth 2 circuit. Here's how I'll do it. I'm just going to make these nice, like an 8x9 matrix C and a 9x8 matrix D, whose product is going to compute S plus U times V transpose. So in C, I'll put S and U, and in D, I'll put the identity matrix, and yeah, you get S plus the U times V transpose. Okay, and we'll count the number of non-zero entries here. In C, it's 22 from S plus 8 from the U, which is 30. In D, it's 8 from the identity plus 8 from the V, which is 16. So now, this gives C has more non-zero entries than D, so the whole size comes from C, and you take the big Kronecker power of it, and you get a circuit for Hn of size 30 to the log base 8 of n, which is n to the 1.64. So this is like symmetrization trick. We really don't want like C to have way more non-zero entries than D. So one thing you can note, if I put the minus sign in the correct place in the definition of the matrix, the Walsh-Hadamard transform is a symmetric matrix. Maybe you might need to permute the columns before that's the case. So we could also write it, for example, as D transpose times C transpose, where the one on the right side has more non-zero entries than the one on the left side instead. And then we can write the 64 by 64 Walsh-Hadamard transform as the Kronecker product of 2 different 8x8 Walsh-Hadamard transforms. One of them we write as C. Okay, I think this should be times, and this should be Kronecker product. Sorry about that. One of them we write as C. No, sorry, this is correct, actually. This is correct, actually. Sorry, this is after applying the mixed product property, yeah. So for one of them we replaced with C times D, the other we replaced by D transpose times C transpose, and then mixed product property says that the whole thing is C Kronecker D transpose times D Kronecker C transpose. That's the whole thing. And we check what is the size of this. Well, it's 30 times 16 to the log base 64 of n, and you put that into your calculator, and it tells you that it's n to the 1.49. There you go. And if you don't have a calculator with you, one thing you can check is if this were 32, then it would be exactly 1.5, and so since it's 30, it has to be something less than 1.5.
Question because of the good luck result. I mean, you said n to the 1.5 is
Yeah.
the lower bound, then you have this bounded coefficient.
Yeah.
Where is it now larger than 1?
Yeah.
Maybe
That's a fantastic question. So the idea is in the S part, some of our entries are 2s and minus 2s. Why is that? I was ready for you. in the S part, some of our entries are 2s and minus 2s. Why is it? Well, U times V transpose has a bunch of 1s and minus 1s, And S has to change that to the Walsh-Hadamard transform. So there are some entries that are 1 but supposed to be -1, so we subtract 2 from them and vice versa. So S has 2's in it. And then when you make the circuit for all n, you take the Kronecker power of this. So some of the entries are going to be products of log base 64 of n 2's, and so they'll be large because of that. Yeah.
In the numbers are the polynomial in n?
Yeah. They're powers of 2. They're at most like n to the 0.25 or something like this. Exactly. Yeah. Okay, so this is really the whole thing. Okay, so let me tell you. Yeah, sorry. Any questions about that? Actually, any other questions?
How to get to into the 1.45?
Oh yeah, let me tell you about that. So I'm not gonna show you the whole proof, but I'll tell you the idea. Okay, it's an idea that Yunfeng Guan and Ashwin Padaki and I introduced called rebalancing, which is it's actually focusing just on this resymmetrization at the very end. So what's the idea? Here's what we were doing. We're basically going to do this symmetrization in a more fine-grained way somehow. So what we were doing before was, we're inductively or recursively building up these circuits. So if we'd previously written the n by n matrix as a circuit x times y, then to make the 8n by 8n circuit, so the Kronecker product with h8, what do? Well, we replace hn with x times y, and then we choose whether to replace the h8 with either c times d or d transpose times c transpose. And the way we're doing is we're just alternating. So we did c times d the first time, then d transpose times c transpose the second time, and so on. So one of them has more non-zero entries on the left, the other has more non-zero entries on the right. So for example, if you choose c times d, you get a Kronecker product like this, you apply the mixed product property, and this is how we're building up our circuit right now. So we're going to do something just a tiny bit more fine-grained like this than this. So we're going to take our current circuit x times y, and I'm going to break it up into the different columns of x and the different rows of y. So I'll call them x1 through xm and y1 through ym. So our current circuit looks like this. It's the sum over all I of xi to y transpose Kronecker h8. And now I'm going to move the Kronecker product with h8 into the sum. So I'll write it like this. So sum over all I of x, the ith gate there, the xi times y transpose Kronecker with h8. And once I do this, now I can make a different choice of whether to use c times d or d transpose times c transpose for each I separately. So basically before we were sort of made the same one choice for all i's, but now I can make a different choice for each I separately, depending on whether xi or yi has more non-zero entries. So if, for example, if you chose ai, okay. I think maybe Honor got swapped or something. But you choose separately for each one. You put this inside the sum. And it lets you get more fine-grained control over balancing separate parts of the circuit. And this is optimizing over this is where the improvement comes from. Actually doing this, I think the idea is simple, but the analysis ends up being a huge mess. Like in this first paper with Guan and Padaki, we had like page-long statements of like you need your original circuits to satisfy these properties and be pretty imbalanced, but not too imbalanced, and blah 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 in order for all the stuff to work. A cool observation that we made in this recent work with my student Baitian Li, basically Baitian made this observation, is that there's this theory of the asymptotic spectrum that was actually developed by Strawson a long time ago. The goal of this theory was to kind of take the ideas behind matrix multiplication algorithms and show that you can generalize them to other situations with recursive structure. And what Baitian found is that the way you analyze these rebalancing strategies can actually be captured by Strawson's theory of the asymptotic spectrum. So we found that actually in this original paper with Guan and Padaki, we were, in hindsight, kind of reproving the special cases of some lemmas from Strawson's theory. So this theory gives like a really nice, clean way to analyze what happens. And if you're familiar with this or you want to know more, I'm happy to chat about it later. But that's the main idea. Okay. So that's the depth 2 circuit. I want to talk about the unbounded depth circuit now. So improving this leading constant from 1 to 0.96 if we don't care about the depth of the circuit. And the high-level idea is very similar to what we've been doing. So we're going to use an improved algorithm for a fixed Walsh-Hadamard transform, in fact, the 8x8 one again, to get an improvement for all Walsh-Hadamard transforms. And you can check the fast Walsh-Hadamard transform algorithm. It computes h8 times a vector using 24 operations, 8 times log base 2 of 8. And our main goal is going to be to improve this just a little bit to 23 operations, sort of. You'll see this is not exactly what we're going to do, but it's close to what we're going to do. And when you apply this recursively, as we'll see, this will give the leading constant of 23 over 24, which is a bit less than 0.96. So that's the whole idea. And our starting point, again, is the same, basically the same rigidity upper bound. So here's the 8x8 Walsh-Hadamard transform. I'm going to decompose it as the sum of a low-rank matrix and a sparse matrix. Actually, this is very slightly different because I put a 1 in the top left entry of the low-ranked part. So it's rank 2 and 21 non-zero entries. But basically the exact same thing we were doing before. And the intuition, like we've been talking about, is a rigidity upper bound like this very naturally leads to an algorithm for doing a matrix vector multiplication. So let's say I wanted to multiply h8 times a vector, whose entries I'm going to call a, b, c, d, e, f, g, and h. What do? Well, we're going to just separately multiply the sparse part times the vector, multiply the low-rank part times the vector, and then add those two things together. So for the sparse part, what do? Well, the top row is all zeros. For the other non-zero rows, each one we just add two things, then multiply by 2. You can see, for example, the second row, we compute c plus e plus g and multiply by 2 to get that second row there. So in total, this will be, there's 7 non-zero entries, and rows rather, and you have 3 operations per row, so it'll be 21 operations to do the sparse part times a vector. For the low-ranked part, you can see, they're all the same on b through h, they just differ on what's going on with a. So you first compute the sum of b through h, and then the first row is a plus that thing, and all the other rows are a minus that thing. So you can do the low-ranked part in total 8 operations, 6 for computing this total variable, and then the a plus and the a minus are the last 2. And then finally you combine them. Generically it would make 8 operations to add the 2 vectors of length 8, but we know for the sparse part, actually the top entry is always 0. So you only need 7 additions to add these 2 vectors together. And in total, you get an operation count of 36, which is great. But I just told you our goal is to beat 24. So we're somehow a little bit off from that. So I'm now this is my favorite part of the whole talk. I'm now going to do a bunch of little arithmetic tricks to decrease this operation count. So yeah, prepare yourselves. Here's the algorithm. Here's the algorithm right now. So we compute this total variable. We compute the difference, a minus that. And the first row is a plus the total. All the others are this difference thing, which is the low-ranked part, plus the sparse part, which is 2 times the sum of 3 variables. You can count that there are 36 arithmetic operations on the slide right now. All right. So I'm going to rearrange some things. The first is that this will end up being very important later on. You can see kind of right near the end of this algorithm, I'm doing lots of multiplies by 2, but I kind of somehow want to do those at the beginning instead. So I'm going to, at the very beginning, actually multiply b through h by 2, and I'll call those new things b prime through h prime. And then when they showed up at the end, I can use the prime variables instead of those original variables. So I've just moved some multiplications by 2 to the beginning. Actually, I haven't changed the operation count at all. I removed 7 over here, and I added 7 over there. Okay, we haven't changed anything yet. Now, I'm going to notice, well, this total variable where we're adding b through h together, some of that work could be reused to do some of these additions that are happening with the variables on the right over here. So for example, let's see, yeah, b prime plus c prime, I'm currently adding them together to get row 5, but it could also be helpful to compute the total variable. So I'm going to compute 3 intermediate things, t1, t2, and t3, which are sums of 3 pairs of those things. And then I'm going to put them in on the right, where they were appearing anyway. So once again, I've just added 3 operations, subtracted 3 operations. I haven't made a change. But now I can save on the operations to compute total. Right now it's 6 additions. But instead, I'm going to add t1, t2, and t3, and the last variable e prime, and divide by 2, and do it with only 4 operations. So I've saved 2 operations so far. We've gone down from 36 to 34. Okay. We're almost there. Okay, another trick like this is, you can see that there are a lot of places on the right where we're adding this variable diff with the same prime variable. Like maybe in row 2 and row 7, both of them, we have a diff plus g prime is something we could compute to help compute that row. So I'm ahead of time going to compute diff plus d prime, e prime, and h prime, and then I'm going to use those to start off the sums of diff and something over here on these 7 rows on the right side. So this was great. I added 3 operations. I subtracted 7 operations. So I saved 4 more, and we got down to 30 operations. Okay. Okay, I'm gonna stop doing this here. So our current operation count is 30 operations. I told you I was gonna get down to 23 operations. But one thing you can notice is that 7 of our operations here are just multiplications by 2, right? Actually when Kevin Rao and I first came up with this, I thought like the way we were gonna sell it in the end is say, oh, you know, multiplications by 2, should be a lot cheaper than like other arithmetic operations. You can do it with a bit shift, so it's like more, it's not saving, but it converted the. Anyway, there's actually a way better trick for kind of getting rid of these multiplications by 2 that I'll show you now. So, right, some of them at the beginning are multiplications by 2. If you could somehow remove those, we'd be at the 23 operations that I promised you. But one nice thing you can notice about our algorithm is that at the very beginning, we multiply b through h by 2, but then the rest of the algorithm doesn't use b through h anymore. It only uses b prime through h prime. So actually, our whole procedure I just gave you can be viewed as a 23 operation algorithm for the problem we were given as input a and 2b and 2c up to 2h, and you want to compute the Walsh-Hadamard transform of a, b, c, d, e, f, g, h. So we're going to think about it in this way and show, actually, this is still sufficient to apply recursively and do the usual Walsh-Hadamard transform. So why is that? Well, I have to show you in a little bit more detail, and I'm going to do this a little bit by analogy by reminding you how at the beginning of the talk we converted an H2 algorithm into an HN algorithm. So here's what the fast Walsh-Hadamard transform looked like from a while ago. Remember, we took our vector, we broke it into 2 parts, we recursively computed their Walsh-Hadamard transform, and then we output their sum and their difference. And the idea is like this sum and difference here looks a lot like the 2x2 Walsh-Hadamard transform. And you can really write it out in this way. So let me rewrite that same thing again. To compute Hn on input v, you let A be the Walsh-Hadamard transform of the first half, you let B be the Walsh-Hadamard transform of the second half. Then the first half of the outputs is their sum, and the second half of the outputs is their difference. This is exactly what we did. And I'm going to again write it again. So on input v, you compute the Walsh-Hadamard transforms of the 2 parts. And then for each I between 0 and n minus 1, the ith entry and the n over 2 plus ith entry is going to be the 2x2 Walsh-Hadamard transform of the ai and bi. You can see this is exactly the same, but now h2 like very explicitly shows up in our recursive algorithm. Return y. Okay, so similarly, you can do the exact same thing and get an hn algorithm out of an h8 algorithm. And what does it look like? To compute hn, you first compute 8 different recursive calls of size n over 8. And then for each I between 0 and n over 8, those like 8 output entries are h8 times those 8 input entries that we just recursively computed. And return y. So if you had a better algorithm for h8, you could just directly plug it in here to improve the whole thing. But we don't have a better algorithm for h8. We have this algorithm for this weird version of h8 in which some of the variables are multiplied by 2. So what we really have is a good algorithm for this, where we like at the beginning got 2 times, like 7 out of our 8 recursive calls gave us 2 times those vectors. So what I'm going to do is just for any power of 2, I'm going to give a separate algorithm that computes 2 to the k times the Walsh-Hadamard transform. So for any k, there'll be a circuit that computes 2 to the k times hn. And it's going to make 1 recursive call to itself on size n over 8, and 7 recursive calls to the next one for the next bigger power of 2 for size n over 8. So you make these calls. This is kind of a different way of saying this thing. Same thing as you're kind of pushing the powers of 2 down the recursion all the way to the end. So this gives a recursion where for any k, the time to compute 2 to the k times hn on the vector of length n is t of 1 is 1 now. Like with before it might have been 0, like you just do nothing. Now you actually have to multiply by a power of 2, so it's 1. This is where all the powers of 2 went. But beyond that, for t of n, you make 8 recursive calls of size n over 8 plus 23 over 24 times n over 8 for doing this 8 by 8 Walsh-Hadamard transform over here. And it indeed solves to 23 over 24 n log n, like I promised you. All right, so that's the algorithm. Okay, there's one last slide I have. I think I have a few more minutes. Okay. So one thing you might be thinking about everything I've told you so far, and certainly I have been thinking this for a long time, is that these algorithms I showed you kind of are combining a bunch of sort of arbitrary steps, right? Like we did calculations. Hopefully I gave you a bit of intuition for why we were doing these things. But nonetheless, like it's not clear we're using the best rigidity stuff. It's not clear we're doing the best rebalancing stuff. Like it's not clear anything is the best that we could be doing. So, you know, for a few years now, my students and I have been trying to improve this, but we've gotten to a weird place where we've instead kind of shown barriers against improving basically every single step of the algorithm I just told you about. So let me tell you a little bit about this. So the first natural question you might ask is, could we use a better rigidity upper bound? Like I showed you this particular 8x8 thing, could we use something better? Right, we used the rank 1 rigidity of the 8x8 Walsh-Hadamard transform. Actually, our follow-up work ends up using the 16x16 and 32x32, like a very natural generalization of the same construction we talked about. You can check, it shows this rigidity upper bound that you can change a little bit less than half of all the entries in the whole matrix, well, 1 over root n fraction less, and make the rank 1. This is what we use. And in this work in this past year with Jingxun Liang, we actually showed our new rigidity lower bound that this is basically tight over finite fields at least. So not only for rank 1, but even all the way up to rank like log n, you basically need to change half of the entries of the whole matrix to drop the rank down to this like some constant times log n. So there's some calculations in the background here, but you can check this. This really shows that you can't. There's no better rigidity upper bound up to rank log n that you could use with this whole approach to improve at all the exponents that we're getting. So weirdly, this 8x8 thing that my code found is really the best one you could be using. There's a little bit of a loophole here in that you can say, what about using rank bigger than log n, which is reasonable. I've been thinking about that a little bit. But actually, one thing that Jingxun and I showed is some barrier, basically, that it's very difficult to prove rigidity lower bounds for ranks bigger than this. If you're familiar with this stuff, there's a big program initiated by Razborov for using rigidity lower bounds to prove communication complexity lower bounds. He usually targets ranks that are much higher than like log n or poly log n. But in the case of Kronecker powers like the Walsh-Hadamard transform, we gave this hardness magnification result, which basically says if you could prove a similar rigidity lower bound for even a slightly higher rank, this would actually like complete the main goal of Razborov's program and show that the inner product nod 2 is not computable by the communication complexity analog of the polynomial hierarchy, whatever that means. This would be like a big deal, much bigger deal than just showing that rigidity upper bounds can't improve this like specific algorithm I gave. So there's somehow like a barrier to proving a barrier against the algorithmic approach I told you about. But I suspect this is not the right way to go. Like I think somehow small constant ranks seemed to be the best way to do these things, and we really ruled this out with the rigidity lower bound we showed here. Okay, so there's that. Another thing you can naturally ask is, could we use better rebalancing or something, right? I showed you we actually improved quite a bit from 1.49 down to 1.45 using these like fine-grained rebalancing tricks. Actually, in this paper with Baitian, we showed that in a very formal sense, which I won't talk too much about now, like the current rebalancing strategy we're using is optimal. Like I told you we use this like Strawson's asymptotic spectrum theory, and one nice theorem about it is this so-called duality theorem, which you can use to sometimes show that what you're doing is optimal in that context. And it actually applies very naturally here to show, in some sense, if you have like a fixed collection of rigidity upper bounds that we have, like the number we're getting right now is the best you could possibly get out of them. So there's a formal sense in which like you really can't improve the numbers in that way either. So you know, there's all this stuff, but nonetheless, you could ask, is there something bigger picture here? You know, we got down from 1.5 to 1.45. How far could you hope to go? You could ask, could we give a new general convincing barrier that you need n log n? Now that I told you, you know, rigidity is not on its own going to prove this. So together with Byton, we proved like a short step toward that direction. So what we proved is assuming the strong exponential time hypothesis, which if you're not familiar with that, it's a popular fine-grained conjecture, which basically says that you can't solve CNF SAT in better than 2 to the n time, roughly. Assuming this, we actually showed there's no depth 2 circuit with size n to the 1 plus little of 1. So there has to be some, you can't like decrease this exponent forever. There has to be some number bigger than 1 that you can't get past. So this is something, I don't know how to prove something like this for higher depth, even depth 3 I don't know how to prove something like this for. But for depth 2 we were able to show this. So there might be some limit, it's not clear what it is. Yeah, one thing I'll mention about this though is that, so we built on this technique of Ryan Williams, and we kind of generalized what he was doing a little bit. But he makes this offhand remark in his paper that perhaps these kinds of circuit constructions are actually a good way to try to refute the strong exponential time hypothesis. So maybe you could see this not as a barrier, but as an exciting algorithmic opportunity. Anyway, I'll leave it at that. Thanks.
Great, we've got plenty of time for questions.
I think you mentioned a reduction from FFT to FWT. Is there like the converse direction?
I don't know anything in the opposite direction. Yeah. It's really weird. Like, you know, the FFT and fast Walsh-Hadamard transform, like the algorithms look very similar to each other. And somehow, other than this one lemma I told you about, I don't really know any like formal reductions between, like it's possible you could get small O of n log n for operations for one of them, and I don't know if that would immediately imply small O of n log n for the other one, for example. Yeah, somehow that like the FFT really has these like steps where you multiply by complex numbers that are like really hard to disentangle from the rest of the operations that make it hard to relate to the Walsh-Hadamard transform. Yeah, but I don't know. I don't know any reduction in the other direction like that. Yeah.
Thank you.
So you got, you know, both the improvements were based on doing something better for the constant size 8 by 8 thing.
Yeah.
Could you go beyond that, especially use things like alpha evolve or something to search for like a better constant size?
Yeah, I've been trying with some of the DeepMind alpha evolve folks. We haven't found anything yet. I don't know. Yeah, I mean this like rigidity thing was like one approach I had to trying to do this. Like basically every other situation in which rigidity arises, it's not like constant constructions of rigidity that matter. It's somehow asymptotic constructions. And I really thought maybe as you picked n growing, like something else would arise you could take advantage of. And we've up to this loophole, whatever, kind of ruled that out. Beyond this, I don't know. I do, yeah. Maybe, I don't know. I guess it would make me happier if like someone in this room improved it rather than our AI overlords, but yeah.
Or someone in the room with our AI overlords.
Perhaps, yeah, a collaboration.
Other questions?
Have you tried to do similar things for disjointness? Let's say because disjointness also has a similar function. I mean, like construct better depth to circuits.
Yeah, depth 2, we do have better depth 2 circuits for the disjointness also. Yeah, there was like it uses very similar techniques. It actually focuses a lot on the rebalancing part and not on the, like rather than using a fixed construction based on rigidity, you use a fixed construction by Yukna and Sergeev in their book. Actually, they give this like nice, basically they partition up the ones into rectangles and you make use of that. So there is a line of work using these same ideas to improve the exponent there also. Like the straightforward exponent is like 1 point. Oh, do I even remember the numbers? Maybe the straightforward exponent is like 1.35 and we improved it to 1.25 or something like that. Yeah. Many of the ideas apply. I don't know how to improve the leading constant when you don't care about depth for disjointness. I think that's a very good open problem that I don't know how to do.
Non-rigidity things for disjointness?
So we know, like for example, we know it's not rigid enough for the Valiant program for lower bounds, but when you're dealing with like constant rank, suddenly the constants become a lot worse. The problem is kind of the disjointness matrix is much sparser in the first place. So you need a much better rigidity upper bound to improve it. And there's like, we know slightly better ones, but actually the same lower bound techniques I mentioned here show like you can't improve on them very much either. So yeah, I don't know any improvements along those lines.
I don't have a question, it's rather a comment, but what you did reminded me very much what one does for studying matrix multiplication. There's this tensor product structure.
Yeah.
And so, I mean, you just take the problem in some small dimension and you improve it somehow. And once you have it, that's enough. Then you run it and you get the asymptotic improvement.
Yeah, yeah.
I don't think I have seen this technique before. And I mean, I know it for matrix multiplication, but this I think the first time that I see it for another series of problems.
Yeah.
Anybody else has done?
Yeah, there is one problem where it famously appeared too, and that's like this improved algorithms for sparse parity learning. Like the k equals 2 case goes by the name of light bulb problem. There is a I think the problem is let's say like there is a data and it's labeled by a parity of 2 bits, and you want to learn it. And there is a natural algorithm that will be quadratic, and there is a sub-quadratic algorithm for this, which you get by some kind of hacking. But once you have the sub-quadratic thing, you can actually improve k-sparse parity learning by tensoring, and then there are better ways to do this.
And is it the same group of people? This light bulb problem, isn't that?
So
Virginia Williams, I don't know.
So this is actually by Greg Valiant,
okay, nice.
also from like 10, 12 years ago.
Yeah.
But
Yeah.
it's impressive. Okay, it was before ChatGPT, but you used computers.
I did use computers, yeah.
Okay.
Yeah. So there's, yeah. I think it's cool. Yeah, I think so. There's this this theory of the asymptotic spectrum that I mentioned. I think it's becoming increasingly popular lately. Like Eurowin and Avi had this.
But we can take that.
Oh, okay. Anyway, it's becoming increasingly popular. I think we're finding more topics that can be captured by this, and my feeling is constructions like this should be helpful in those situations too. So I'm hoping we'll find more examples in the near future.
Maybe one last question.
Hey, did you try if this makes a difference in implementations of F15?
A little bit. So yeah, I mean, my student Kevin Rao implemented it, and it indeed has the smaller operation count, and his Python implementation of one is better than his Python implementation of the other. There's like the one thing is the implementations people use are very heavily engineered. You don't want to just decrease the operation count. You also care about taking advantage of your cache well and dealing with the communication costs of the algorithm and various things like this. So the idea I had when we came up with this is that, of course, we'd find more improvements soon, and then once we improved it quite a bit more, then we would, team up with engineers. But we're still all stuck on that first step.
And put it up on your site.
Yeah, exactly.
Thanks.
Yeah.
All right, let's thank Josh again.